So taking all that vocabulary from the last video and actually applying it to situations takes some getting used to. It's going to be pretty tough at first. So if you feel like you catch on pretty quick, you're doing a really good job with it. Um, but once it finally clicks, it's just so easy to work with them from that point on. So if you find it hard at first, which you probably will, don't lose hope. So we're going to start talking first about concave mirrors. So let's say we have a boy, and his height is h. He's standing at distance d away from a concave mirror, and by tracing the light rays that come from the top of his head, we can see that his reflection would be a distance d prime from the mirror. So let's scroll down a little bit and look at that. So we have the boy, height h. We have him standing a distance d away from a mirror. So you can see how d is measured from the boy all the way over to the vertex. So it's not just where it, like the closest point of the mirror, we're going to measure it from the vertex of the mirror. So that light ray comes in, bounces off, gets reflected down through the focal point, and then we have another another ray. It comes down through the focal point, gets reflected parallel to the principal axis. So from those two light rays, we can see kind of where they get focused here. Um, they meet up just a little bit behind, a little bit below where the focal point is. So the rays all pass through there. The image of the boy is actually forming at this location where they all meet. So a distance d prime away from the vertex of the mirror, and he has a height h prime. So a little bit different, you can tell. The little grayed out boy shape is smaller, and also he's upside down. So this is kind of like um, a concave mirror is kind of like a spoon. If you've looked into a spoon, you look like you're upside down. So that should be something that's kind of familiar for you. So this image that we've formed, the little grayed out upside down boy, is at distance d prime, and this image is what we would call a real image. So a real image, like we can see in the ray diagram, is formed by actual rays of light. They bounce off the mirror and the actual rays are getting focused, or they all come and meet together at this certain point. So if we had a little screen and we held it up at d prime, an actual upside down shrunken image of a boy would appear on it. So you might have noticed the way that a concave spoon can cast light as you move it at certain angles, and that's because concave mirrors are projecting real images. I don't know if you guys have ever been wearing a watch or maybe on your cell phone, how it kind of bounces the light off and you can focus it into a point. A spoon can do the same thing. So you'll notice we're only able to create a real image when the boy is behind the focal point, behind point F. So what's going to happen if he stands in front? Alright, so I'm going to try my darndest here to draw with my little trackpad. Alright, so we have our spherical mirror here. I can get a good principal axis right there. Alright, so let's say our focal point is right here. Oh, okay, that's a pencil. Here we go. Alright, focal point right here. And then we'll get our boy in here. Alright, so he is inside the focal point. So if we try to come in and draw these light rays, remember we're going to focus on just the top of his head. Really, when you get down to it, there's light rays reflecting off every part of his body. But to get an idea of the image, we only need to look at a couple of them. So comes in, we'll look at one that goes parallel to the principal axis at first. It's going to get reflected through the focal point. Kind of. My drawing's a little bit off, apparently. Okay. Alright, so I made my guy a little bit too big. I had to shrink him down a little bit. But I can't remember where I left off. So we were saying we have one ray coming parallel to the principal axis, gets reflected down through the focal point. Our next ray, though, if you look up above, it went from the head down through the focal point. We can't do that here because the focal point is behind him. We can't go down through and into the mirror. So what we're going to do is to go from the top of his head. We're going to pass right through our mirror. Let me draw in a tangent so we can see it a little better. So we have our tangent line at some point on the mirror. Wow, this is rough with PDF. So our next line is going to come from the top of his head. And it's going to pass through the mirror, but it's going to have no angle of incidence. So technically it doesn't pass right through the mirror, but it would hit at 90 degrees, have no angle of incidence. So you can see if I extended this line out and tried to keep it at the same angle here, then our rays are only getting farther and farther apart, not closer together like they're supposed to form an image. So what we're going to do now is pretend like this one actually extended through the mirror here. I grabbed the wrong one. So we'll pretend this went right on through, and they are actually, quote unquote, meeting behind the mirror. So what we have here is a situation, oh my gosh, like this. Ugh. Alright, so we have an image forming where our lines meet, but it's actually looks like it's happening behind the mirror, and they happen at a higher place. So we've taken this boy and given him a much larger image. So let's try to throw some word explanation behind that because PDF drawings are terrible. Alright, so the lines of this ray diagram, like I said, they don't converge. They don't come together at any point in front of the mirror. They can't because he's inside the focal point. So we can't have any real image forming. There's not any real light rays that would bounce off the mirror and come together. So a concave mirror is only going to be able to project real images of objects as long as they are behind the focal point, or we could say at a distance greater than the focal length, little f. But like we did up in the image above, we can take those diverging lines, so these lines that move farther and farther and farther away from each other and trace them back to the other side of the mirror. I'm going to throw in a better picture because mine is rough. Oh, and it's going to do that. Alright, I'm going to pause again and clear out some of this trash. Alright, so he's in front of the focal point. You can see the ray that bounces off the mirror down through the focal point. The other one, since we can't go through the focal point, goes from the top of his head. And that beam, this is one we were talking about, hits along the normal, so no angle of incidence, and it would reflect straight backwards. So that's how we got from going this way to extending it out that way and finding that these two were divergent. They would never run into each other. Then what we did from there, since they never met on this side, we traced them back on the other side of the mirror. So you can see the dotted lines are an extension of, if they really could pass right through the mirror, they would be going this way. So we can trace diverging lines back behind the mirror to determine the position and size. You can see the giant boy on the other side, and we call that a virtual image. So, like an ordinary, just flat plane mirror, the image looks like it's standing behind the mirror. So it looks like, there's another you standing on the other side. But it's not coming from actual real light rays. No light is focused on some certain point behind the mirror. You couldn't hold up a screen behind a mirror and expect an image to pop up on it. So generally with mirrors, an image is going to be real if it's in front and made of actual light rays, and it's going to be virtual if it's behind the mirror and kind of made up from those imaginary dashed line light rays. So in this one, our virtual image is right side up, so he's on the same side of the principal axis. He is a distance d prime away from the vertex and stands at a height h prime, which would be greater than h. So you can actually test this yourself if you find a nice round spoon. So as you hold it a certain distance away from your face, you can see yourself upside down, so that would tell you that you're outside of the focal length. So if you bring it slowly and slowly closer, your upside down image kind of distorts and disappears. It gets blurred and turns into just a mess. I realize for some of you, you feel like it may have looked that way before, but you'll know what I'm talking about when you see it. So once you pass that certain point, you'll see a much larger reflection, so it kind of blows up on your nose. But now you're right side up, whereas before you were upside down. So the image changes from upside down, tiny you, to right side up, giant you, as soon as your face has crossed the focal point.